Now, today I will just introduce something small and innate to our power factor. But before I start calculating power factor, I want to play a very small video so that we can understand what power factor is and why it is important in AC. Mambo ya alternating current na voltage. So please let me know whether you can see the screen and whether you can hear whatever is being said.
Hey there guys, Paul here from the engineeringmindset.com. In this video we're going to be discussing power factor. We're going to start off really easily with some simple analogies to help you understand the basics, and then we'll advance it into electrical engineering terms with some worked examples, as well as looking at what is power factor, what is a good and bad power factor, what causes bad power factor, and how to fix bad power factor. So what is power factor? Power factor is a unitless number used in alternating current circuits. It can be used to refer to a single piece of equipment such as an induction motor, or for the electricity consumption of an entire building. In either case, it represents the ratio between true power and apparent power, the formula being PF equals kW divided by kVA. So what does that mean? My favourite analogy to explain this is to use the beer analogy. We pay for beer by the glass, but inside the glass there is both beer and foam. The more beer we have, the less foam there will be, so we get very good value for money. If there is a lot of foam, then there's not a lot of beer, and so we're not getting very good value for money. The beer represents our true power, or our kW, our kilowatts. This is the useful stuff we want and need. This is what does the work. The foam represents our reactive power, or our kVAR, kilovolt amps reactives. This is the useless stuff. There will always be some, we have to pay for it, we can't use it, so we don't really want much of it. It does actually have a use and a purpose, but we'll see why later in the video. The combination of these kW, our kilowatts, and a kVAR, the kilovolt amp reactive, is our apparent power, or our kVA, meaning the kilovolt amps. Power factor is therefore the ratio of useful power, or true power, in kilowatts, our kW, divided by what we're charged for in kVA, the kilovolt amps. So it's telling us how much value for money we're getting for the power we consume. If we briefly touch on electrical engineering, and I will keep this part brief, then we might see this expressed as a power triangle. In this case, I'll draw it as a leading power factor as it's easier to visualize. The beer, or true power, is the adjacent line. Then we have the foam, which is the reactive power, on the opposite. Then for the hypotenuse side, which is the longest side, we have the apparent power. This is at an angle from the true power. The angle is known as theta. You see, as the reactive power, or the foam, increases, then so does the apparent power, or the kVA. We could then use trigonometry to calculate this triangle. I won't in this video as I'm just covering the basics, so we'll just see the formulas you need, but we'll do some calculations and worked examples later in this video. If we look at a typical residential electricity bill, then we'll typically see just a fee for the amount of kilowatt hours used, because the power factor and the electricity consumption will be very low. So electricity companies tend to not worry about this. However, on commercial and industrial electricity invoices, especially buildings with smart or interval electricity meters, then we'll likely see charges and information for the amount of kilowatts, kilowatt hours, kilovolt amps, and kilovolt amps reactive used. Large buildings in particular will often see reactive power charges in there, but this depends on the electricity supplier and the agreement they have with the consumer. The reason they charge a penalty for this is because when large consumers have bad power factors, they are increasing the current flow through the electricity network and causing voltage drops, which reduces the supplier's distribution capacity and has a knock-on effect for the other customers. Cables are rated to handle a certain amount of current flowing through them. So if a lot of large consumers connect with bad power factor, then the cables could overload. They could also struggle to meet the demand and the capacity agreements, and then no new customers will be able to connect until they either replace the cables or install additional cables. Reactive power charges occur when the power factor of a building falls below a certain level. This level is defined by the electricity supplier, but it typically starts around 0.95 and below. A perfect power factor would be 1. However, in reality, this is almost impossible to achieve. We'll come back to this part later in the video. In large commercial buildings, the overall power factor is likely to sit in the following categories. Good power factor is generally between 1 and 0.95. Poor power factor is anything from 0.95 and 0.85. Bad power factor is anything below 0.85. Commercial office buildings are usually somewhere between 0.98 and 0.92. Industrial buildings could be as low as 0.7. We'll look at what causes this shortly. Let's first have a look at an example. If we compare two induction motors that both have an output of 10 kilowatts and are connected to a 3-phase 415 50Hz supply, one has a power factor of 0.87 and the other with a power factor of 0.92. Both motors will deliver 10 kilowatts of work, but the first motor has a lower power factor compared to the second one, meaning we're not getting as much value for money. The first motor will need to draw 11.5 kVA from the electricity grid to provide the 10 kilowatts of power. The second motor will need to draw just 10.9 kVA from the electricity grid to provide the same 10 kilowatts of power. This means the first motor has 5.7 kVArs and the second motor has just 4.3 kVArs. Remember, our kilowatts is the beer and that's the useful stuff. The kVArs are the foam, that's the not so useful stuff. The kVA is what we're going to pay for, and that's the kilowatts and the kVAr combined. How did I calculate that? For kVA, I used kilowatts divided by power factor, so 10 divided by 0.87 to get 11.5 kVA. For kVAr, I used the square root of kVA squared subtract kilowatt squared, so the square root of 11.5 kVA squared minus 10 kilowatts squared. We could have also found the power factor from the kilowatt and the kVA using 10 kilowatt divided by 11.5 kVA. We could have found the kilowatts from the power factor and the kVA using 0.87 divided by 11.5 kVA to get 10. So what causes poor power factor? In most cases, the power factor is affected by inductive loads. If we have a purely resistive load, such as an electrical resistive heater, then the voltage and the current waveforms would be in sync or very close. They would both pass through their maximum and minimum point and then pass through the zero axis at the same time. The power factor in this case is 1, which is perfect. If we drew a phasor diagram, then the voltage and current would be parallel, so all the energy drawn from the electricity supply goes into doing work, in this case creating heat. But if we took an inductive load, such as an induction motor, then the coil's magnetic field holds back the current and results in a phase shift where the voltage and the current waveforms fall out of sync with each other, so the current passes through the 0 point after the voltage. This is referred to as a lagging power factor. Earlier in the video I said the foam or the kVAr is useless. That's not exactly true. We actually need some reactive power to create and maintain the magnetic field which rotates the motor. The reactive power is wasted in the sense that we get no work from it, but we still have to pay for it, although we do need it to be able to do the work in the first place. If we drew a phasor diagram for a purely inductive load, then the current would be at an angle below the voltage line, meaning not all the electricity consumed is doing work. If we took a purely capacitive load, then the opposite happens to the inductive load. The voltage and current are out of phase, except this time the voltage is held back. This causes leading power factor. Again, this will mean that not all of the electricity being used is being used to do work, but we still have to pay for it regardless. If we drew a phasor diagram for a purely capacitive load, then the current line would be at an angle above the voltage line as it's leading. Correcting poor power factor. What can we do to correct poor power factor and reactive power charges? In most cases, we come across lagging power factor caused by inductive loads. To correct poor power factor, we can add capacitors or inductors to the circuit, which will realign the current back into phase and bring the power factor closer to 1. If we have a lagging power factor caused by high inductive loads in the circuit, then we add capacitors. If we have a leading power factor caused by high capacitive loads, then we add an inductive load to the circuit. These need to be calculated, and we'll see some example calculations of this at the end of the video. So why should we fix poor power factor? Poor power factor means you need to draw more power from the electricity network to do the same amount of work. Therefore, the cables need to be larger, so the installation is going to cost more money. If the power factor becomes too low, then the electricity supplier might charge you a penalty fee or a reactive power charge. Poor power factor can cause losses in equipment like transformers and leads to high heat gains. It can lead to voltage drops and can even reduce the life expectancy of equipment in extreme scenarios. Capacitor calculations for power factor correction.
I don't know if you've been able to hear what was happening. Tumesikia chochote ama hiyo imetupita tu hivyo?
Mimi nimesikia chochote kidogo.
Now, kwa wale ambao walikuwa na sisi tukianza, Esther, Edwin, Mary, Irene, what have you understood by the term power factor?
Just tried a bit.
Umeelewa nini kuhusu power factor?
Maybe I've learned more or studied more.
Now, are you able to see clearly? Mnaona vizuri? Okay. Is it clear?
Yeah, it's clear.
Okay, in short, power factor katika AC is not something that it's something we have to consider. Kumbuka katika zile vitu tumekuwa tukiongea. Now, for example, we have been talking about voltage and current being in phase and out of phase, and I think katika hiyo video umeweza kuona vizuri. If voltage and current ya AC are in phase, ni kumaanisha kwamba let's say this is voltage and this is current. What it means is that the voltage and current of that alternating source zinafika maximum, zinafika minimum and zero at the same time. Okay? Now, when we talk about AC, kumbuka we were introducing we introduced other components. We had inductors and we had capacitors. Remember, when we are in an industrial use, tutakuwa tunatumia motors.
We
will be using motors and other components. And these motors will increase. When you have mfano a motor katika when connected to a circuit, you'll find that this motor will increase its inductive reactance. I think we have seen this katika zile calculation. Inductive reactance. Kwa mfano, you have a resistor and then you have an inductor in an AC circuit. This, let's say, for example, this AC circuit, the source is producing 100 volts at 50 hertz. The frequency is 50 hertz, and the value of the resistance is, let's say, 50 ohms, and the value of inductance, in this case, is let's say 80 millihenries. You find that in a motor, kwa sababu motor ni coil, utapata kwamba a motor ni coil ambayo imezungushwa around a core. This coil has internal resistance, mfano 50 ohms, and because it has been coiled, then we have to include the property of inductance. Now when you pass AC current, kwa mfano ina motor, utapata kwamba the property of inductance or capacitance in a motor will make the current and the voltage of that AC source to lose its phase. Utapata kwamba the voltage can lead, we had mentioned this last time, can lead or lag the current. Utapata kwamba in this waveform current itakuwa inakuwa produced before or after the voltage. And we have seen that in terms of a phasor diagram. Kwa mfano, if it is a totally resistive circuit, ni resistor pekee ambayo imekuwa connected, as a resistor only has been connected to an AC source. If you draw this in terms of a phasor diagram, a phasor diagram ni ile ambayo tulikuwa tunaongelea when you have a vector rotating around a fixed axis and you represent it as a phasor diagram, you'll find that voltage and current are in phase. They are in phase. But once you introduce kwa mfano an inductor in a purely inductive circuit, you'll find that the voltage, I mean the current, the current will be lagging voltage at 90 degrees. Utapata kwamba waveform ya voltage itakuwa inakuwa produced before the current. And if it is a purely capacitive circuit, then the current is leading the voltage. This means that the current waveform, ile waveform ya current hapa itakuwa inakuwa produced before for a capacitive circuit, and for a inductive circuit then the waveform will the current will be produced after the voltage. Now this is the effect of these components, the inductor and the capacitor. So we have to take into consideration this the angle, that angle ambayo the current and voltage lags or leads each other. We had talked about it na tulikuwa tumeita phase angle. We had called it phase angle. Now power factor, the power factor we represent the lagging or the leading of that current the leading or lagging of the AC current or voltage. Now we have seen that power factor is given by apparent power. No, it is not apparent power. It's true power over apparent power. Now, what is true power? We have heard that true power, in mfano, you are being supplied 50 by KPLC. Katika industry yako unakuwa supplied 50 kilovolt amperes. This is the volt amperes is the unit for apparent power. Please note this. Volt amperes is the unit for apparent power. Watts or kilowatts, watts is the unit for true power. And volt ampere reactive is the unit for reactive power. Is a unit for reactive power. Now you'll find that when KPLC supplies you, for example, 50 kilovolts amperes, out of these 50, whatever you will be using in your industry ama in your machines, the true power, ile power ambayo inatumika na your machines will be, let's say, 45, 30, depending on your application. Let's say 45. 45 is the true power, the one that is being used by the machines. Now this reactive power, or it's known as the useless power, 5 kilovolt, 5 is not being used to do any work. Haitumiki na machine yoyote. That's why we call it useless power. But now once KPLC supplies you with the 50, hata kama unatumia only 45 or 30, you will still have to pay for this useless or reactive power. Sawa sawa. Now if you have a high reactive power, and you have been given that analogy, the beer analogy, or you can use coffee ama soda, umelipia, let's say 1,000 shillings for 1 cup of coffee or soda. Acha tuchukue soda. Umelipia 1,000 shillings for a cup of soda ama a bottle of soda. If this is the amount of the soda, hiyo ndio soda katika kikombe chako, and then we have ile foam hapo. In terms of power, the total in your cup will be the apparent power. The total amount of soda or coffee in your cup will be known as apparent power. The actual amount of soda ambayo unakunywa ni true power in terms of power. True power. Na ile pofu, the useless, ile ambayo utakunywa ni reactive power. When you consider in terms of power. Okay? Now, when you pay for 1,000 shillings for a soda, wewe na mtu mwingine mnalipia the same amount for the soda. Na utapata kwamba huu ambaye analipia kuna ule ambaye hii ndio his true power, and this is reactive. Kuna ule ambaye has a less amount of soda than you, this being the total apparent power. You'll get that you who has more soda in your cup will have better value for the 1,000 shillings that you have paid for. You who has more soda has better value for the 1,000 shillings you have paid for, as compared to yule ambaye the amount of soda in his cup is let's say half. And when you talk about this in terms of power, utapata kwamba both of you are paying for 1,000 shillings, but you are using for that amount of 1,000 shillings. For that amount of 1,000 shillings, wewe we are using more power, true power, to power your machines, as compared to huyu ambaye let's say he's using a half of his soda ama of his power. Both of you are paying the same amount. Now, this person who has a higher reactive power will be charged more. Kuna penalty ambayo KPLC tamlipisha. Why? When you have a higher reactive power, this means that you are drawing. You will be drawing more power into your industry. Now, why will KPLC charge you? That means that if you're drawing more power into your industry, inamaanisha kwamba KPLC will have to install bigger transformers. KPLC will have to introduce larger wires so that they can accommodate that higher power being drawn into your industry. Now, we have seen that power factor is true power in kilowatts or watts divided by apparent power, which is in volt amperes or kilovolt amperes. If you represent this in terms of a triangle, kuna kitu ambayo inaitwa power triangle. You'll find that the power factor is this angle, and this is the apparent power or the total power being supplied to you by the supply company, your distributor. This is the true power, the actual power that you are consuming in your machines, and this is the reactive power, the useless power. It is useless in terms of that you're not using it to do any work. It is there, but you have to pay for it. Now, if you have a bigger reactive power, what will happen? You'll find that this angle will increase. Kama reactive power yako ni kubwa, utapata kwamba this angle will increase. If you have a reactive power ambayo ni kidogo, utapata kwamba this angle yako will reduce. Na tukiingia katika mambo ya hesabu, ukiangalia in this case, when you take a value in a rectangle and you say adjacent divided by the hypotenuse, what are we finding? When you take adjacent divided by the hypotenuse, because when you look at this formula, we are saying that power factor is true power divided by apparent power. Ukiangalia in terms of hesabu ama trigonometry, adjacent over hypotenuse ni nini? Cos. Are we together? So the power factor in a power triangle is the cosine of this angle, which is given by the true power divided by the apparent power. Are we together? Tuko pamoja?
Yes. Umesema power factor.
Power factor is the cosine of this angle, which is formed by the triangle. This is known as the power triangle. Power triangle, and its value is true power divided by apparent power. Sawa. If let's say you're given an angle, this is 50.37, and you're told to find the power factor of that when you're told to find the power factor, you just take the cosine of this angle. If you're given the value of true power and you're given the value of apparent power, then you can say that the power factor is true power over the apparent power. Are we together? Now, the reason why we don't want a high... Now, when you do your calculation, you'll find that power factor ranges from 0 to 1. Okay, final calculation, ukapata that your power factor is more than 1, or it is less than 1, then umeanguka. There is something wrong with that calculation. So it will always range from 0 to 1. Now, in an industry, umeona katika hiyo video amesema in a household situation, power factor doesn't come into play. But when you're in an industry and you have inductive loads, inductive loads ni kama motors, utapata kwamba your power factor will range, itakuwa ina range, and the introduction of inductive loads increases, it will increase the reactive power. The presence of inductive loads in an industry increases the reactive power. So if you have a high power factor, or you have, let's say, if you have high reactive loads, kama you have a high reactive loads, this means that this angle increases. Sindio, this is reactive, this is apparent, and this is true. Are you able to see? Naona vizuri? No. Okay. Now, I was saying, if this value of reactive power increases, then this means that your angle increases, ndio? Hii reactive power increase, hii angle itaongezeka. Right? Angalia the differences between these two triangles. This angle is smaller than this. So if you have a larger angle, then this value increases and your apparent power also increases. Sindio? And if this angle ni ndogo, then your reactive power decreases and your apparent power decreases. Now, when you have a large reactive power, your supplier or steamer will charge you more. Not because you're using more power, the total power. No, it's because a lot of that power is going to waste. Watakupenalize. Hello? Are you able to hear me? Kwa sababu napotea kidogo. So nikipotea, please let me know, and if you can see the diagrams vizuri niambie pia, kwa sababu kuna shida ya network on my side. Is it clear? Kama bado ina shida kidogo.
Iko sawa.
Mnaweza ona?
Yeah.
Okay. Now, how do we calculate power? I mean power factor. There are so many ways you can calculate power factor. The one that I've shown you is by using the power. Tumetumia power to calculate power factor. This is apparent power, This is reactive power. And this is true power. Now, how do we calculate power factor? We have seen that power factor is the cosine of this angle that is formed by this is the power triangle. That is the first way of calculating power factor, by using the power triangle. Is the cosine of that angle, which is true power in kilowatts or watts, divided by the apparent power, which is in volt amperes. Now, katika hesabu, if you're given true power and you're given reactive power, how will you find apparent power? Umepatiwa true power and you have been given reactive power. How do we find apparent power?
Sokotoa.
No, like hujapatiwa, utatumia sokatoa, lakini nataka uniambie in terms of, kuna ile kitu hesabu, Pythagoras theorem. Pythagoras theorem. I don't know the spelling. True power squared plus reactive power squared is equals to apparent power squared. Now, how will you find apparent power? You will take the square root and the square root of that, si ndio? Mpaka hapo tuko sawa? Kwa mfano umepatiwa the value of true power is 50 kilowatts, and the value of reactive power is, let's say, 100 kilovolts reactive. Na umeambiwa utafute the power factor. You can find the power factor by finding the angle. Nilisikia mtu akitaja tan mahali. That is correct. You can still find using tan. But now, you can also find it by finding the apparent power mwanzo, and then you take the true power divided by the apparent power. Now, apparent power in this case will be 50 squared plus the reactive, which is 100 squared, and then you find the square root. That will give you the apparent power. Itakuwa 50 squared plus 100 squared, and you find the square root. That gives you that the apparent power is 111.803 kilovolts amperes. I want you to please note these units. When you talk about power factor, kama unatumia power, then the true power is in kilowatts or watts. The apparent power is in kilovolt amperes or volt amperes, and then the reactive power is in kilovolt ampere reactive or volt ampere reactive. That is the units. So that will give you the apparent power as 111. Therefore, the power factor is the true power divided by the apparent power, which is equals to true power ni ngapi? Is 50 kilowatts divided by the apparent power, which is 111.803. 50 divided by 111.803. That gives you a power factor of 0.4472. Now, if you are to represent this as an angle, you will take the cosine, the cos inverse of that 0.4472. Now, do we know how to find the cos inverse using a calculator? Tunajua kutafuta cos inverse ukitumia calculator.
Yes.
Shift kisha ufinya cos.
Yes.
Now the cos inverse of that is 63.435. That is a power factor in terms of degrees. Now, when that is finding the power factor in terms of power using the power triangle, you can also find the power factor using something known as the impedance triangle. You'll find that the value, of course, I mean the triangles will be similar, and even finding the angle will be similar. But now this will be, it won't be true power. This will be, let's see, resistance R. This will be impedance Z, impedance, and this will be XL or XC. XL, now let's talk about XL. This will be inductive reactance. Power factor, when using the impedance triangle, will be equal to R over Z. R over Z. Are we together? Will be the resistance of that circuit, the value of the resistor in that circuit over the total resistance, and in this case, to December, the total resistance is known as impedance, which is still cos of this angle. When you say adjacent divided by the hypotenuse, bado ni cos. Now this is fine in power factor in terms of using the impedance triangle. We can also find power factor using the voltage triangle. If you have in a, we'll see an example. Now, when you use this voltage triangle, it occurs similar to the other triangles. But now here, we'll have the voltage being used, the voltage drop in the resistor. This here will be the voltage drop in the inductor. And this here will be the total voltage in that circuit. Kwa mfano, let me draw an AC circuit that has a resistor and an inductor connected. And we saw that power factor sana is brought about by inductive loads. We have a resistor and we have an inductor connected in series. You'll find that, let's say this one, the supply voltage is 50 to 40 volts at a frequency of 50 hertz. Is it clear? Am I imepotea kidogo?
It's clear.
Okay, now then the voltage drop across the resistor, let's say, is 100 volts, and the voltage drop across the inductor is, let's say, ngapi? 120. No, ama 140. Is 140 volts. Then using the voltage triangle, we can determine the power factor by saying that the power factor, using this voltage triangle, you can say that the power factor will be equal to the voltage. Let me draw the voltage triangle again. This is the total voltage. This is that angle. This is the voltage across the resistor and the voltage across the inductor. The power factor will therefore be the voltage across the resistor divided by the total voltage in that circuit. The voltage across the resistor in this case is 100 volts, upper VR, and the voltage and the total voltage in our circuit is 240 volts. So our power factor will be 100 divided by 240, which gives us a power factor of 0.4167. If you represent this power factor in terms of an angle, it will be the cosine of that angle. Shift cos of that angle, itakupatia 65.376 degrees in terms of angle. Now, what I want you to notice is this. As this angle increases, hii angle ikiendelea kupanda, mfano, let me draw it like this. At this value of, as our angle here increases from 0 mpaka 90, you'll find that our power factor will be reducing from 1 to 0. What do I mean? Upper, a purely resistive circuit that has the voltage and the current in phase. that means that the angle here is 0. Oh no. Can you hear me? Okay, you're able to hear me now and you can see clearly. You can hear me clearly and you can be able to see. I hope. Tunaona? Na unanisikia vizuri? Nilikuwa nasema in these triangles hizi ambazo nimechora, the power triangle, the impedance triangle and the voltage triangle, this angle ambayo iko hapa, as it increases, you'll find that our power factor will decrease from the perfect power factor, which is 1, to 0, which is the worst. What do I mean? At a perfect power factor, the voltage and the current are in phase. So the angle in this case hapa is 0. So if we take the cosine of 0, itakuwa ni ngapi? If you take the cos of 0, you'll find that our power factor is 1. Are we together? So that is a perfect power factor. But in industrial ama in real situations, it is very rare to find a perfect power factor because of those inductive loads, the motors and the like. So you'll find that our power factor, as this angle increases, so ikitoka from 0 iendelee ku increase mpaka ile wakati itafika cos 90. Cos 90 is 0. And when you have a power factor of 0, this is the worst power factor you can ever get. So if when angle ikiendelea ku increase from 0, 20, 30, 40, utapata that our power factor is decreasing from 1 to 0. Now, let us do an example so that we can see how to calculate power factor. Is there a question up to that point? Kuna swali? There's no question?
No.
Okay. Now, we have been given a circuit up. It is from one of the examples we did before. You have been given the frequency of supply is 800 Hertz. You have been given that the voltage supply, AC supply, is 100 volts. Umepatiwa that the value of the resistor here is 300 ohms, and the value of the inductor is 80 millihenries. Ukambiwa, number 1, find the current flowing in that circuit, and number 2, find the power factor. You find the power factor. Now, how do you find the current? How do you find current? I think we did, we have already done the part ya current. Ukitumia Ohm's law, given voltage, voltage is given by current times resistance, and in this case we'll call it impedance because we have inductive reactance present. So we will no longer call it resistance. The total resistance of this circuit will be called inductive reactance. Now, Current, therefore, will be given by the voltage divided by the total resistance, the impedance. Now, how do we find the impedance in these circuits? Tulikuwa tunatafuta impedance namna gani? You take the value of the resistance plus. Now, when you're finding the value of impedance, what I want you to understand is I had given you that the impedance in this is an RL circuit, a resistor inductor circuit. In such a circuit, the Z is given by R squared plus XL squared, and then you find the square root. Now, what we have done, the formula impedance for all those circuits RLC ni hiyo. What we do, mfano katika hii circuit yetu, since it's an RL circuit, then we'll have inductive reactance. We'll have inductive reactance, but our capacitive reactance will be equal to 0. So this, therefore, Z will be equal to resistance squared plus the inductive reactance squared. Now, how do we find XL? XL is given by 2 times pi times the frequency times the value of the inductor. Now, XL, therefore, will be given by 2 times pi times what is the value of our frequency? 800 times the value of our inductance, and you have been given that it is 80 millihenry. So when you convert it to Henry, itakuwa 80 divided by 1000, or 80 times 10 raised to the power negative 3. Now the value of our inductive reactance will therefore be 2 times pi times 800 times 80 divided by 1000. Our inductive reactance is 402.124 ohms. Now, how do we find the value of Z, the impedance? It will be the value of the resistance squared, and the value of the resistor is 300 ohms, plus the value of the inductive reactance, and we have found it to be 402.124 squared. So the impedance will therefore be given as 300 squared plus whatever you got squared, then you find the square root to give you the value of impedance as 501.7 ohms. Now, the current flowing in our circuit will be the voltage supply divided by the total resistance according to Ohm's law. The supply voltage is at 100 volts divided by impedance, the total resistance in our circuit, which is 507 ohms. So 100 divided by 507 ohms gives you the value of current in our circuit as 0.19932 amperes. That is just a revision of the calculation we did. Now, something else we had mentioned before, ilikuwa phase angle. How do we find the phase angle? The angle at which the current and voltage are lagging or leading each other, those waveforms. Phase angle is given by the tan inverse of how do we find the phase angle? The tan inverse of the inductive reactance divided by the value of the resistance. Remember, when you draw the impedance triangle, we have this value over here, or it can be phi or it can be theta. You'll find some books have written it as phi and it can be theta. So this is the impedance, this is the resistance, and this is the inductive reactance. For a capacitive circuit, then it will be opposite, because it is a leading. The phase angle will be leading, the power factor will be leading. So this will be the value of the impedance, this will be the value of the resistance, and this will be the value of the capacitive reactance. Now, when you talk about phase angle, the value of the angle that the current is leading or lagging the voltage, then you'll take the tan inverse. Tan inverse is opposite over adjacent. So the tan of that angle, whether it's theta or phi, will give you the phase angle. The tan inverse of this angle will give you the phase angle. Now, the power factor. The power factor in this case will be the value you got. Power factor will be the value you got of it will be the resistance divided by the impedance. The power factor will be the resistance divided by the impedance. Now, the value of resistance, what will be the resistance? We have been given as 300. The impedance that you have calculated will be 501.7. Therefore, our power factor will be 300 divided by 501.7. You get that the value of our power factor is 0.597 or 598. That is the value of our power factor. Are you together? If you are to represent your power factor as an angle, then you will take the cos inverse, shift cos of that value to get the value of the power factor as an angle, which is 53.228 degrees. Are we together?
Yes.
Any question? Is there a question?
Mwalimu, mimi sijaelewa.
Hujaelewa wapi?
Hapo mali calculation nimeanza nayo.
Unajua sasa hii calculation ni ya ile tulikuwa tumefanya when we started AC circuit. Kwa mfano umechorea hiyo circuit ukaambiwa the source voltage source hapa ni 100 volts being supplied at a frequency of 800 hertz. The value of the resistor is 300 ohms. The value of the inductor is 80 millihenry. Remember katika AC circuits we introduced other components, passive components, a capacitor and an inductor. Hapo unakumbuka?
Ndio.
Tukasema kwamba when you introduce these components, an inductor and a capacitor, when we are finding the total resistance, we call it impedance. Now, kutegemea na the configuration ya circuit, you might find that a resistor and a capacitor have been connected in series. We have a resistor and a inductor connected in series. We have an inductor and a capacitor connected in series, or we have all of them connected in series. Hiyo inakumbuka?
Ndio, nakumbuka.
Tukasema kwamba how we find mfano you've been given a circuit and then you've been told to find the current flowing in that circuit. Using Ohm's law ambayo inasema that the voltage is equals to current times the resistance. In an AC circuit then this is voltage is equals to the current times the impedance. Sawa sawa?
Ndio.
Now how do we find impedance in these circuits? Tukasema kwamba impedance is given by the square root of resistance plus XL minus XC squared, and we call this inductive reactance, and this is capacitive reactance. Now reactance is how a capacitor and an inductor oppose the flow of current in an AC circuit. Remember, a resistor, how does it oppose flow of current in a circuit? It does that by resistance. A resistor has resistance, but when you introduce a capacitor and an inductor, we don't call that resistance. We call it reactance. Now the combined effect of reactance, whether it is inductive or capacitive, na resistance, it gives you impedance. We say that impedance is the total resistance of a circuit due to the ohmic resistance, your value resistance, na the reactance, whether it is inductive or capacitive. So the impedance is given by the resistance plus. Now, if it is an inductive circuit, ambayo imekuwa tu connected to an inductor, then the value of the capacitive reactance is 0. If it is a capacitive circuit, then the value of the inductive reactance is 0. In our case here, we have an inductor connected. Kwa hivyo our capacitive reactance is 0. So how do we find impedance? You'll get that impedance is given by the value R squared plus XL squared. Now how do we find inductive reactance? Ni 2 times pi times F times L. Tukasema kwamba now frequency tulipatiwa kama 800. Inductor value yake tulipatiwa kama 80 millihenry. 80 millihenry, and we have to convert it to Henry. So how do we convert 80 millihenry to Henry? It is 80 divided by 1000, or 80 times 10 raised to power negative 3. They mean the same thing. We find that the value of our inductive reactance is 402.124. Kwa hivyo impedance, the total resistance in our circuit will be the resistance squared, which is 300 squared, plus 402.124 squared. Kwa hivyo impedance ni 501.7. Now, if you are told to find the current flowing in our circuit using Ohm's law, kumbuka Ohm's law ni V is equals to IR, but now in our case R is Z, impedance. So therefore, current is equals to V divided by the total resistance, the impedance. The voltage had been given as 100 volts, and the current, the total impedance, tumepata as 501.7. Therefore, the current flowing in our AC circuit is 0.19932 amperes. Phase angle, we had done this before. Phase angle is given as the tan inverse of the inductive reactance XL over the resistance, the value of the resistance. So itakuwa, in this case, itakuwa the value of our inductive reactance is, what did we get? XL, 402.124 divided by the value of the resistance, which is 300. The value that you get, 402.124 divided by 300, when you find the tan inverse, shift tan of that answer, that will give you the phase angle, 53.2728 degrees. That is the angle that the voltage and the current are out of phase with each other. Remember, tumekuwa tukisema phase sana sana. Tukisema that if an angle, if the AC is in phase, ni kumaanisha kwamba the waveform, ile waveform ya current na voltage will be reaching maximum. This is voltage, this is current. Will be reaching maximum, will be reaching zero, and will be reaching minimum at the same time. That means that this voltage and current are in phase. But when you introduce vitu kama inductor na capacitor, this changes. So utapata kwamba the current ama the voltage will be lagging or leading the other. And that angle that shows that the current and voltage are leading or lagging each other is known as the phase angle, and it is found by taking the tan inverse in this triangle, this impedance triangle, the tan inverse of this divided by this. Are you together? When you take the tan inverse of that and that, itakupatia the phase angle. Now the power factor. The power factor is given by the value of the resistor over the value of the total impedance, the total resistance in that circuit. The value of our resistor was 300. The value of our resistor was 300. The value of the total resistance, the impedance, we calculated and found it as 501.7. Therefore, our power factor will be 300 divided by 501.7 to give you 0.597 as the power factor. If you find the cos inverse of that 0.95, it will give you the same, the phase angle, 53.28. The angle that the voltage or the current is lagging or leading each other. Tumeelewa?
Yes.
Are you together? Kuna swali mpaka hapo? No question. Now that is finding the power factor in terms of the impedance triangle. Kwa mfano, you have been given a question ukaambiwa that let's see. You've been told that the power being supplied into your... No, let us reach there for now. What I will do is I will send you examples, the power factor in AC circuits. Then ile power factor tukitumia power, then we'll do them later. Sawa sawa. Kuna swali mpaka hapo? We'll do power factor when we use power triangle baadaye. Let us understand using the impedance triangle. Now, you have been given another circuit kama hiyo. This is an RC circuit. You have a resistor and a capacitor connected in series. Ukaambiwa that the value of the resistor is 50 ohms. The value of the capacitor is 1.5 microfarads. The value of the alternate source is 60 volts being supplied at 2.5 hertz. Had we done this example before? Sijui kama tulikuwa tumefanya, but let us do it. Now, you've been told to find the number 1, the current flowing through the circuit, and number 2, the power factor. The power factor flowing in that circuit. Now, how do you find the power factor? No, how do you find the current? V is equals to IZ. Now, therefore, the current will be V divided by Z, which is the total resistance. Now, how do you find the value of impedance, some of the total resistance in such a circuit? Remember, it is R squared plus XL minus XC squared. Now, since this is we have a resistor and a capacitor, there is no inductor. Therefore, our inductive reactance in this case will be 0. Therefore, this will be Z is equals to R squared plus minus XC squared. Sawa. Now, remember, when you square a negative number, it becomes positive. But I'm just writing it as it is here. Now, Z. No, not Z. XC. How do we find XC? The capacitive reactance. Tutaipataje? We have done this before. How do we find XC? We said that we find the XL as 2 pi FL. Now, how do we find XC? Inaonekana tukifanya examples watu wanafunga vitabu mpaka the next class. XC is given by 1 over 2 times pi times the frequency times the value of the capacitor. Now, this is 1 divided by 2 times pi times the frequency of supply is 2.5 hertz. So 2.5 times the value of the capacitor. But it has been given in microfarads. Micro, which is times 10 raised to power negative 6 or divided by a million. So changing it to farads, itakuwa ni the value of the capacitor, which is 1.5 divided by a million. Micro. 1.5 divided by a million. So the value of our reactive capacitance itakuwa 1.5 divided times 10 raised to power negative 6 times 2.5 times 2 times the value of pi. So when you take that divided by 1 divided by that value, it gives you the value of the reactive capacitance as 42,000. Let's see. Forty-two. No, I made a mistake. This value is in kilohertz. The supply frequency. This is in kilohertz. So let me start again. So this is the value of the capacitive reactance is 1 over 2 times pi times change in kilohertz to hertz is you multiply by 1,000. So 2.5 times 1,000 will change to hertz, and then change in microfarads to farads is by you divide by a million. So 1.5 divided by a million, or we multiply by 10 raised to power negative 6. Therefore, the value of x will be, so 1.5 divided by a million times 2500 times 2 times pi. Voila. Times 2, answer, times 2 times pi. When you take that value divided by 1, we'll get that the value of the reactive capacitance, no, the capacitive reactance is 42.441 ohms. That is the value of XC. Now the impedance will therefore be R squared plus minus XC squared. So Z is given by the value of the resistance you have been given as 50 ohms. So 50 squared plus, now we have found the XC as 42. So it will be negative 42.441 squared. So Z is 50 squared is 2500 plus, when you square a negative number, so negative 42.441 squared, it gives you a positive, what have I done? Negative 42.441 squared. It gives you a positive number. So plus 1801.24. So when you add those two plus 2500, then you find the square root. It should give you the value of the impedance, which is 65.584 ohms. So what will be the current in our circuit? The current flowing in our circuit. The current will be given by the supply voltage divided by the total resistance, which are the impedance. The voltage supply was 60 volts. The impedance, the total resistance, is 65.584, giving you a current of 60 divided by that answer that you got. It gives you that the current flowing in that circuit is 0.9149 amperes. Now, the power factor. The power factor will be given by the R, the value of the resistor, divided by the value of the impedance value that you have gotten. The value of the resistor is 50 ohms. And the value of the impedance is 65.584. That gives you a power factor of 50 divided by 65.584. That gives you a power factor of 0.7624. Tuko pamoja? Are we together?
Yes.
Now, what I want you to do is you go through those examples again. Your video nilituma katika Google Classroom, so I don't know whether you are able to see it. I've also sent another video to show you how to calculate power factor.